All right. Hey, what's up and what's up, man? Another day to get into this. I'm so excited to jump back into Eloquent JavaScript, and I'm just so excited. So, today we're moving on to chapter 3 functions. Welcome to the read along. Let's go. Okay. People think that computer science is the art of geniuses, but the actual reality is the opposite. Yes, many people doing things that build on each other, like a wall of mini stones. That's Donald Knuth. I think he's the father of algorithms. I saw his interview just lately. He has the big book of algorithms. Mm. So let's look at the illustration. This illustration here has is talking about is looking at bees. Here's some bees and maybe fans. This is a fan, some type of plants, and I wonder what it means. The other ones had tentacles, and I think it was talking about bindings. So curious to see what this illustration is about. We'll refer to this in the end. So functions are the bread and butter of JavaScript programming. The concept of wrapping a piece of program in a value has many uses. It gives us a way to structure larger programs, to reduce repetition, to associate names with subprograms, and to isolate these subprograms from each other. The most obvious application of functions is defining new vocabulary, creating new words. In prose is usually bad style, but in programming it is indispensable. Typical English speakers have some 20,000 words in their vocabulary. Few programming languages come with 20,000 commands built in, and the vocabulary that is available tends to be more precisely defined and thus less flexible than human language. Therefore, we usually have to introduce new concepts to avoid repeating ourselves too much. Defining a function. A function definition is a regular binding where the value of the binding is a function. Alright? A function definition is a regular binding where the value of the binding is a function. For example, this code defines square to refer to a function that produces the square of a given number. Const square will be the function, and then this is what will run return x times x, and then console log square 12 will give us 144. A function is created with an expression that starts with the keyword function. So how do you know a function? It starts with the keyword function. Functions have a set of parameters, in this case only x, and a body, which contains the statements that are to be executed when the function is called. The function body of a function created this way must always be wrapped in braces, even when it consists only of a single statement. A function can have multiple parameters or no parameters at all. In the following example, make noise does not list any parameter names, whereas power lists two. So this is the const make noise, and then the function, it is been wrapped in the brace console log pling, and then make noise, when you call it make noise, it will give you pling. Const power is equals to the function, and then we have a base, the exponent, and then let result be 1 4. So in here inside this function, we are now writing this program, and we are creating a binding called result. So let result be 1, 4, and we're creating a loop. 4, let count be 0. This is when we start the count, and the count is less than the exponent. This is when we'll stop when it's less than the exponent. Add 1 count, and then the result. Then we print, you return the result times or equals the base. Then close, then you tell it return result. I think I've read this correctly, and then you close it out. So console log power 2 and 10 will be 10, 24. So power 2 raised to 10, which is the base, and the exponent will give us 10, 24. What I've just noticed is that a function has other programs wrapped in it. Some functions produce a value such as power and square, and some don't, such as make noise, whose only result is a side effect. A return statement determines what the value the function returns. When control comes across such a statement, it immediately jumps out of the current function and gives the returned value to the code that called the function. A return keyword without an expression after it will cause the function to return undefined. Functions that don't have a return statement at all, such as make noise, simply return undefined. So let's look at this. All right, let's see. We're going to run it in our CodePen. Control V. What will it return in the console? Nothing. It will return playing in the console. All right, clear. Excuse me, clear. Let's look at the other one. All right, const command C. Let's run it in our JavaScript environment. Let's collapse our CSS editor and collapse our HTML editor. Alright, it has given us 10, 24. Alright, so this code works. How about if we said is 3 raised to the power of 10? What happens? That will be 59,049. And I think the beauty of programming and computers is that it would take you years to calculate this, but it gives you in less than a second. All right. Some functions produce a value, and can we make these changes on our website? Let's try and see what happens. Okay. All right, nothing actually changes on our website, but there's no problem. There is no problem. Let's move on. So some functions produce a value such as the power and the square, and some don't, such as make noise, whose only result is a side effect. A return statement determines the value the function returns. When control comes across such a statement, it immediately jumps out of the current function and gives the returned value to the code that is called the function. A return keyword without an expression after it will cause the function to return undefined. Functions that don't have a return statement at all, such as make noise, simply return undefined. Parameters to a function behave like regular bindings. but the initial values are given by the caller of the function and not the code in the function itself. Bindings and scopes. Each binding has a scope, which is the part of the program in which the binding is visible. For bindings defined outside of any function or block, the scope is the whole program, and you can refer to such a binding wherever you want. These are called global scope, global binding. But bindings created for function parameters or declared inside a function can be referenced only in that function. So they are known as local bindings. Every time the function is called, new instances of these bindings are created. This provides some isolation between functions. Each function call acts in its own little world called its local environment and can often be understood without knowing a lot about what is going on in the global environment. Bindings declared with let and const are in fact local to the block that they are declared in. So if you create one of those inside of a loop, the code before and after the loop cannot see it. In pre-2015 JavaScript, only functions created new scope. So old style bindings created with var keyword are visible throughout the whole function that they appear in, or throughout the global scope if they are not in a function. Let x be 10, and if true, we're going to run our program. Let y be 20 and z be 30. Console log x plus y plus z, and you will indeed get 60 because this is the local environment. And but they tell us y is not visible here. So we've moved out of this environment, this local environment. So when you call outside the environment console.log x plus z, it will give you 40. Why? Because it is now a local. This is a global environment and not the local environment. Okay, that is cool. Okay, each scope can look out into the scope around it. So x is visible inside the block in the example. X is visible in this block in this example. The execution is when multiple bindings have the same name. In that case, code can see only the innermost one. For example, when the code inside the half function refers to n, it is seeing its own n and not the global n. This is a lesson in local environments and global environments. So const have, which is a function n, and we're going to return n over 2 and then close it. Then you say let n be 10, and then console log have 100, it will give you 50. But when you say console log n, it will give you 10. Why? Because 10 is not in that this n is outside this environment. All right, is that right? Yes, that is right. Good. Nested scope, and this is where it begins to be very important to understand functions. And I remember when I read through this before, it was very hard for me to get my head around it. But let's go. Nested scope. JavaScript distinguishes not just global and local bindings. Blocks and functions can be created inside other blocks and functions, producing multiple degrees of locality. For example, this function, which outputs the ingredients needed to make a bunch of hummus, has another function inside it. Alright, so const hummus, we are going to create a function of factor where we'll have a const ingredient, which is the function of amount, unit, and name. And then inside this function, we'll have the let ingredient amount be. We are going to start amount times factor. If ingredient amount is more than 1, unit plus or equal to s as a string. Console.log ingredient amount, unit, and name. Ingredient 1, and then we're going to have this string can chickpeas, ingredient 0.25 cup tahini, ingredient 0.25 cup lemon juice, ingredient 1, then clove garlic as a string, ingredient 2, then tablespoon olive oil, ingredient 0.5 teaspoon cumin. The code inside the ingredient function can see the factor binding from the outer function, but its local bindings such as unit or ingredient amount are not visible. This unit or ingredient amount, they are not visible to the outer function called factor. The set, and when we run this, can we get anything? It's hard to tell because I don't see how we can console log it. We have not called it to the console log, so will it produce anything? Technically nothing, because we need to either call it or return it for us to get something. But it's good to understand this. The code inside the ingredient function can see the factor bindings from the outer function, but its local bindings such as unit or ingredient amount are not visible to the outer function. The set of bindings visible inside a block is determined by the place of that block in the program text. Each local scope can also see all the local scopes that contain it, and all scopes can see the global scope. This approach to binding visibility is called lexical scoping. Lexical scoping. Okay, that's a new idea being introduced here. Functions as values. A function binding usually simply acts as a name for a specific piece of the program. Such a binding is defined once and never changed. This makes it easy to confuse the function and its name. But the two are different. A function value can do all the things that other values can do. You can use it in arbitrary expressions and not just call it. It is possible to store a function value in a new binding, pass it as an argument to a function, and so on. Similarly, a binding that holds a function is still just a regular binding and can if not constant, be assigned to a new value, like so. Let's look at this. Let launch missiles, so we've defined a new binding, launch missiles, be a function, this is the function, missile system.launch now. If safe mode, launch missiles will give us the function, and inside this function we're going to do nothing. In chapter 5, we will discuss the interesting things that can be done by passing around function values to other functions. Okay, a declaration notation. There is a slightly shorter way to create a function binding. When the function keyword is used at the start of a statement, it works differently. So, function square x, and then we'll pass in return x times x, close it. This is a function declaration. The statement defines the binding square and points it at the given function. It is slightly easier to write and doesn't require a semicolon after the function. There is one subtlety that with this form of function definition, console.log, the future says, then we're going to call future. Function future, then we're going to ask it to return you'll never have flying cars. If we run this on our thing, the future says you'll never have flying cars. So we've defined this function future, we've called it, and then we've asked it to return you'll never have flying cars. And this is interesting because I think this console log should have come down here, don't you think? Where we could say the future says you'll never have flying cars. It's interesting. Maybe they'll explain to us why this console log came above and not beneath. The preceding code works even though the function is defined below the code that uses it. Function declarations are not part of the regular top to bottom flow of control. They are conceptually moved to the top of their scope and can be used by all that code in that scope. This is sometimes useful because it offers the freedom to order code in a way that seems meaningful without worrying about having to define all functions before they are used. And this is also a powerful idea that we have added in understanding how function declarations are used in context of the scope. Arrow functions. There's a third notation for functions which look very different from the others. Instead of the function keyword, it uses an arrow, and this arrow is an equals and a greater than sign, made up of an equals sign and a greater than sign, not to be confused with the greater than or equals operator, which is often written as a greater than or equal operator. All right, so const power will be equal to a function of base and exponent, and then wanted to return this, to work out this inside it. Let result be 1, we're defining a for loop here. And then for, let start our count at 0, and then going to stop at the exponent, and then add count, then result equals times base, and then return result. This is the same function that we saw here. This is the same function that we saw here. Const power and function of a base exponent, but this time they removed the word function and they've replaced after this parenthesis with the arrow function. Then let result be 1, and then they have worked through the for loop. Okay, where is it? Here where it is. The arrow comes after the list of parentheses and is followed by the function's body. It expresses something like this input, the parameters, produces this result. All right, this input produces this result. When there's only one parameter name, you can omit the parentheses around the parameter list. So, all right, you could, okay, so let's first read this. When there's only one parameter name, you can omit the parameters around the parameter list. If the body is a single expression rather than a block in braces, that expression will be returned from the function. So these two definitions of square do the same thing. Const square 1, arrow function of x, we want it to return x times x. And this is the other one, square 2, is going to be x and an arrow function that will return x times x. A mental note to myself, what we've been learning in JavaScript all along from chapter 1 is how to abstract words into a shorter form of writing it and explaining it. When an arrow function has no parameters at all, its parameters list is just an empty set of parentheses. So const hon is just empty, and then console log, it will return to the console log toot. There's no deep reason to have both arrow functions and function expressions in the language, apart from a minor detail that we'll discuss in chapter 6. They do the same thing. Arrow functions were added in 2015 mostly to make it possible to write small function expressions in a less verbose way. We'll be using them a lot in chapter 5, and it's important also, another personal note to self, to understand this idea of a less verbose way, because my experience now is we are getting less and less verbose in our understanding of this syntax. The call stack. The way control flows through function is somewhat involved. Let's take a close look at it. Here's a simple program that makes a few function calls. So a function of greet of who is going to give us, and we're going to the console log to return hello plus who. All right, and so when we say greet Harry, and then console log bye, hello Harry, bye, that's what it should print. Let's run that. Right, hello Harry, bye. It has given us those two outputs of those strings in our code. A run through this program goes roughly like this. The call to greet causes control to jump to the start of that function, which is line 2. The function calls the console log, which takes control, does its jobs, and returns control to line 2. Then it reaches the end of the greet function, so it returns the place that is called it, which is line 4. And that line after that calls the console log again. After that, it returns, and the program reaches its end. We could show the flow of control schematically like this. Not in function, in greet, in console log, in greet. Not in function, in console log, not in function. It's interesting that it has gone back to not in function. Because a function has to jump back to the place that called it when it returns, the computer must remember the context from which the call happened. In one case, console.log has to return to the greet function when it is done. In the other case, it returns to the end of the program. The place where the computer stores this context is called the call stack. The call stack. This is something to do with the JavaScript language. Every time a function is called, the current context is stored on top of this stack. When a function returns, it removes the top context from the stack and uses that context to continue execution. Storing this stack requires space in the computer's memory. When the stack grows too big, the computer will fail with a message like out of stack space or too much recursion. The following code illustrates this by asking the computer a really hard question that causes an infinite back and forth between two functions. Rather, it will be infinite. If the computer had an infinite stack, as it is, will run out of space. Below is stack. Alright, function chicken and return egg. Okay, and then function of egg return chicken. Console log chicken came first, and it will just go back and forth and back and forth and back and forth and back and forth and back and forth, and I think it will break. But let's try that. Let's run that on our console and see what happens. Control C, and let's paste in our console and hope our computer and our session doesn't break. Alright, and caught range error. Maximum call stack size exceeded at egg, at chicken, at egg, at chicken, at egg, at chicken, at egg. Amazing. The reason I say this is because when I was learning loops in the last lesson, I called an infinite loop and my computer froze. That was a good thing to learn. Optional arguments. The following code is allowed and executes without any problem. Function of a square x, it will return x times x. Console log square, 4 true, and the string hedgehog. It will give us 16. We define square with only one parameter, a number value. Yet when we call it with 3, the language doesn't complain. It just ignores the extra arguments and computes the square of the first one. JavaScript is extremely broad-minded about the number of arguments you pass to a function. If you pass too many, the extra ones are ignored. If you pass too few, the missing parameters get assigned the value undefined. The downside of this, it is possible, likely even, that you'll accidentally pass the wrong number of arguments to functions and no one will tell you about it. The upside is that this behavior can be used to allow a function to be called with a different number of arguments. For example, this minus function tries to imitate the minus operator by acting on either one or two arguments. Function minus a or b, and what we want it to do is if uh, that's a loop, b is equal, strictly equal to undefined, return minus a, else return a minus b. Console log minus 10, it will give us 10, it will give us negative 10. And then console log minus 10 and 5, we have given it two values, it will give us 5. Interesting. It has given us, it has returned a minus a on 1, and at the same time it also has returned minus 5. So if you write an equals operator after parameter followed by an expression, the value of that expression will replace the argument when it is not given. For example, this version of power makes its second argument optional. If you don't provide it or pass the value undefined, it will default to 2 and the function will behave like a square. Alright, so function of power, base, and exponent is 2. Alright, let result be 1. For creating a for loop here, then we're going to ask it to return result, and then we're going to call the console log of power of 4, it will give us 16, and we're going to call the console log power of 2 and 6, it will give us 64. Let's make sense of this. Alright, so this, it will give us two actual results, which makes it weird that it gives us two different results. In the next chapter, we will see a way in which a function body can get at the whole list of arguments when it is passed. This is helpful because it makes it possible for a function to accept any number of arguments. For example, console.log does this. It outputs all the values it is given. Console.log string C, string O, string 0, and 2. It will give you C or 2. Closure. The ability to treat functions as values, combined with the fact that local bindings are recreated every time a function is called, brings up an interesting question. What happens to local bindings when the function call that created them is no longer active? The following code shows an example of this. It defines a function called wrapValue that creates a local binding. It then returns a function that accesses and returns this local binding. The function wrapValue will be n, and we want it to create a binding called local, which is n, and then it will return a function of local. But let wrap1 be the wrap value of 1 and let wrap 2 be the wrap value of 2. Then we're going to say console log wrap 1, it will give us 1, but console log wrap 2 will give us 2. This is allowed and works as you'd hope. Both instances of the binding can still be accessed. This situation is good demonstration of the fact that local bindings are created anew for every call, and different calls can't trample on another's local binding. This feature, being able to reference a specific instance of a local binding, is an enclosing scope called closure. A function that refers bindings from local scopes around it is called closure. This behavior not only frees you from having to worry about lifetimes of bindings, but also makes it possible to use function values in some creative ways. With a slight change, we can turn the previous example into a way to create functions that multiply by an arbitrary amount. So, a new function called a multiplier factor that will return the number of a function where the number is times a factor. Let twice multiplier 2. Console log twice 5. Alright, so here we have created this function, and here we have defined this variable twice, and we've asked our console log to twice this 5, which is a function. So it will remember this and will remember this. Interesting. The explicit local binding from the wrap value example isn't really needed, since a parameter is itself a local binding. Thinking about programs like this takes some practice. A good mental model is to think of function values as containing both the code in their body and the environment in which they are created when called. The function body sees the environment in which it's created, not the environment which it is called. In the example, multiplier is called and creates an environment in which its factor parameter is bound to 2. The function value it returns, which is stored in twice, remembers this environment. So when it is called, it multiplies its argument by 2. Okay, so that was closure. Now we look at recursion. It is perfectly okay for a function to call itself, as long as it doesn't do so often that it overflows the stack. A function that calls itself is called recursive. Recursion allows some functions to be written a different style. Take, for example, this alternative implementation of power. Function of power, inside the function power you have a base and an exponent. And then inside it, if the exponent is 0, return 1. Else, return base times power, base exponent n minus 1. Then we jump out of it. Console log power of 2 raised to 3 is 8. This is rather close to the way mathematicians defined exponentation, and arguably describe the concept more clearly than the looping variant. The function calls itself multiple times with the ever smaller exponents to achieve the repeated multiplication. But this implementation has one problem. In typical JavaScript, implementation in typical JavaScript implementation, it's about 3 times slower than the looping version. Running through a simple loop is generally cheaper than calling a function multiple times. The dilemma of speed versus elegance is an interesting one. You can see it as a kind of continuum between human friendliness and machine friendliness. Almost any program can be made faster by making it bigger and more convoluted. The programmer has to decide on an appropriate balance. In the case of power function, the inelegant looping version is still fairly simple and easy to read. It doesn't make much sense to replace it with a recursive version. Often though, a program deals with such complex concepts that giving it some efficiency in order to make the program more straightforward is helpful. Worrying about efficiency can be a distraction. It's yet another factor that complicates program design, and when you're doing something that's already difficult, that extra thing to worry about can be paralyzing. Therefore, always start by writing something that's correct and easy to understand. If you're worried that it's too slow, which it usually isn't since most code simply isn't executed often enough to make any significant amount of time, you can measure afterwards and improve it if necessary. Recursion is not always just an efficient alternative to looping. Some problems really are easier to solve with recursion than with loops. Most often these are problems that require exploring or processing several branches, each of which might branch out again into even more branches. Consider this puzzle. By starting from number 1 and repeatedly either adding 5 or multiplying by 3, an infinite set of numbers can be produced. How would you write a function that, given a number, tries to find a sequence of such additions and multiplications that produces that number? For example, the number 13 could be reached by first multiplying by 3, then adding 5 twice. Whereas the number 15 cannot be reached at all. Here's a recursive solution. Function find solution and is of a target, and inside it we want it to be another function find current and history. Inside that, if current is equal to target, I want you to return history. Else, if current is greater than target, return null. Else, return find current plus 5, then history plus 5, close that, or, that's the logical or, find current times 3 and history times 3, close it, jump out of it, return find 1 string, close. Console log find solution of 24, and it will give you 1 times 3 plus 5 times 3. Notice that this program doesn't necessarily find the shortest sequence of operations. It is satisfied when it finds any sequence at all. It is okay if you don't see how this works right away. Let's walk through it since it makes a great exercise for recursive thinking. The inner function find does the actual recursing. It takes 2 arguments, the current number and a string that records how we reach this number. If it finds a solution, it returns a string that shows how to get the target. If no solution can be found, starting from this number, it returns null. To do this, the function performs one of 3 actions. The current number is the target number. The current history is a way to reach that target, so it is returned. If the current number is greater than the target, there is no sense in further exploring this branch because both adding and multiplying will only make the number bigger, so it returns null. And finally, if we are still below the target number, the function tries both possible paths, that is starting from the current number and calling itself twice, once for addition and once for multiplication. The first call returns something that is not null, it is returned. Otherwise, the second call is returned regardless of whether it produces a string or null, because it's from the past. So, to better understand how this function produces the effect we're looking for, let's look at all calls to find that are made when the search for a solution for the number 13. Going to find 1 and 1, then find 6, which is 1 plus 5, find 11, which is 1 plus 5 plus 5, then find 16, no, that's too big, find 33, no, that's too big, find 18, no, that's too big. Okay, now find 3, which is 1 times 3, find 8, which is 1 times 3 plus 5, then find 13, which will be 1 times 3 plus 5 plus 5. I found it. The indentation indicates the depth of the call stack. The first time find is called it start by calling itself to explore the solution that starts with 1 plus 5. That call will further recurse to explore every continued solution that yields a number less than or equal to the target number. Since it doesn't find that one and hits the target, it returns null back to the first call. The logical OR operator causes the call that explores 1 times 3 to happen. This search has more luck its first recursive call through yet another recursive call hits upon the target number. That innermost call returns a string, and each of the logical OR operators in the intermediate calls passes that string along, ultimately returning the solution. Right? Growing functions. And I think I'm going to stop here because I have to step out, and we're going to come back and start from growing functions as a part B. However, we only have a shorter, or we could just finish. Right. There are two or more or less natural ways for functions to be introduced into programs. The first is that you find yourself writing similar code multiple times and you prefer not to do that. Having more code means more space for mistakes to hide and more material to read for people trying to understand the program. So you take the repeated functionality, you find a good name for it, and you put it into a function. The second way is that you need some functionality that you haven't written yet, and that sounds like it deserves its own function. You'll start by naming that function, and you'll write its body. You might even start writing code that uses the function before you actually define the function itself. How difficult it is to find a good name for a function is a good indication of how clear a concept it is when you're trying to wrap. Let's go through an example. You want to write a program that prints two numbers, the number of cows and chickens on a farm, with the word cows and chickens after them and zeros padded before both numbers so that they can always be 3 digits long. 007 cows and 011 chickens. This asks for a function of two arguments, the number of cows and the number of chickens. So let's get coding. Function print farm inventory of cows and chickens. Inside it, we're going to create a string. Let cow string be string cows, while cow string length is less than 3. Inside that, we want cow string to be 0 plus cow string. Console log cow string cows. Let chicken string chickens, while chicken string dot length is less than 3, similarly to our thing. Then console log chicken string chickens. print farm inventory 711, and let's run this code. Control C. I'm going to post it into our code pen. Command V. And we're going to allow it to refresh. It would have been easier to just run it in the console. Not now. 007 cows, 007 chicken. Alright, cool. While .length, writing .length after a string expression will give us the length of that string. Thus, the while loop keeps adding zeros in front of the number strings until they are at least 3 characters long. Mission accomplished. But just as we are about to send the farmer the code along with a hefty invoice, she calls and tells us that she also started keeping pigs, and couldn't we please extend the software to also print pigs? Oh, we sure can. But just as we're in the process of copying and pasting those 4 lines one more time, we stop and reconsider. There has to be a better way. Here's our first attempt. Now create a function, print 0 padded with label. Going to have number and label. Let number string be string and pass the number, while here is a loop. A number string dot length is less than 3. Inside that we're going to pass the number string will be 0 plus the number string, and then console.log number string and label. Function print farm inventory cows, chickens, pigs. Print 0 padded with label cows, chickens. Print 0 padded with label chickens, chickens. Print 0 padded with label pigs, pigs. Print farm inventory 7, 11, and 3. It works, but that name, print 0 padded with label, is a little awkward. It conflates 3 meanings: printing, 0 padding, and adding a label into a single function. Instead of lifting out the repeated part of our program wholesale, let's try to pick out a single concept. Function 0 pad is going to have number and width. And we're going to say let string be a string of a number, while string.length is less than width. Inside that, we're going to pass string is equal to 0 plus string, and then we return string. And then function print farm inventory cow, cows, chickens, and pigs. Inside that, we're going to console.log 0 pad cows 3 and cows. Console.log 0 pad chickens 3 and chickens. And then similarly for pigs, 0 pad pigs 3 and pigs. Print farm inventory 7, 16, 3. A function with a nice obvious name like 0 pad makes it easier for someone who reads the code to figure out what it does. And such a function is useful in more situations than just a specific program. For example, you could use it to help print nicely aligned tables of numbers. How smart and versatile should our function be? We could write anything from a terribly simple function that can only pad a number to 3 characters wide, to a complicated generalized number formatting system that handles fractional numbers, negative numbers, alignment of decimal dots, padding, different characters, and so on. A useful principle is not to add cleverness unless you're absolutely sure you're going to need it. You can be tempted to write general frameworks for every bit of functionality you come across. Resist that urge. You won't get any real work done, you'll just be writing code that you never use. Functions and its side effects. Functions can be roughly divided into those that are called for their side effects and those that are called for their return value. Though it's definitely also possible that both have side effects and return value. The first helper function in the farm example, print 0 padded with level, is called for its side effect. It prints a line. The second version, 0 pad, is called for its returned value. It is no coincidence that the second is useful in more situations than the first. Functions that create values are easier to combine in new ways than functions that directly perform side effects. A pure function is a specific kind of value providing function that not only has no side effects but also doesn't rely on side effects from other code. For example, it doesn't read global bindings whose value may change. A pure function has the pleasant property that when called, the same argument is always produces the same value and doesn't do anything else. A call to such a function can be substituted by its return value without changing the meaning of the code. When you're not sure that a pure function is working correctly, you can test it by simply calling it. And you know that if it works in that context, it will work in any context. And pure functions tend to require more scaffolding to test. Still, there is no need to feel bad when writing functions that are not pure or to wage a holy war to purge them from your code. Side effects are often useful. There'd be no way to write a pure version of console.log, for example, and console.log is good to have. Some operations are also easier to express in an efficient way when we use side effects, so computing speed can be a reason to avoid purity. Alright, summary. This chapter taught you how to write your own functions. The function keyword, when used as an expression, can create a function value. When used as a statement, it can be used to declare a binding and give it a function as its value. Arrow functions are yet another way to create functions. So like to define f to hold a function value, say const f is function a. To declare g to be a function, we can also say function g, a and b. And also a less verbose way, let h be a arrow function a return 3. A key aspect in understanding functions is understanding scopes. Each block creates a new scope. Parameters and bindings declared in a given scope are local and not visible from outside. Bindings declared with var behave differently. They end up in the nearest function scope or the global scope. Separating the tasks your program performs into different functions is helpful. You won't have to repeat yourself as much, and functions can help organize a program by grouping code into pieces that do specific things. Wow, that was a doozy. Alright, so we're going to look at the exercises in a short while, but we will be done for now because I have to step out. So stop recording.